Hello, everyone. Thank you very much for being here. My name is Manny from Consumer Electronics Test and Development, and I'll be your host for this afternoon. As I'm sure most of you know, Consumer Electronics Test and Development magazine is the world's foremost magazine that looks at all the latest test, inspection, and certification solutions for consumer electronic devices. I would like to offer a warm welcome to everyone who is in attendance here at this webinar, which is presented today by Nicholas Jones, Principal Technical Lead from CSA Group. Thank you for being here today. I'm very shortly going to hand you over to Nicholas. Once again, thank you very much for being here. We can't wait to hear from you. Please also be aware that after the presentation, there will be the opportunity to ask questions in a Q&A session. So please have questions ready. I'm sure those of you attending will have questions today. If so, please add them to the Q&A box and we'll endeavour to answer them at the end. So the subject matter for our webinar today is navigating compliance and standardization of USB-enabled appliances. Nicholas will be exploring the safety compliance challenges for manufacturers using USB in appliances, focusing on the key technical differences in end product applications and discussing ongoing standardization efforts. So, without further ado, I'll hand you over to Nicholas.
Hello, and welcome to the CSA Group presentation navigating the compliance and standardization of USB-enabled appliances, particularly focused on the safety compliance challenges of utilizing USB between different end product applications. During this presentation, we shall navigate the key safety concerns around the use of USB, highlighting the significant differences in the compliance of similar use end product standards commonly used in domestic applications, and discuss some of the open issues still under development within the standards committees. The main focus will be on the end product standards for appliances, the IEC 60335 series. As part of this webinar, I shall start by providing a brief summary of my background, then talk through the evolution of the USB interface, summarize the existing diversity of USB applications in appliances, including possible new opportunities for use, introduce the applicable standards and some of the safety measures implemented, touch on the regulatory implications and the benefits in use of USB to sustainability, detail the standards landscape with an overview of the similar end product standards, explain some key variances in the safe-to-touch criteria and shock assessments, highlight the misconceptions and key safety focus of ingress protection, describe some recent enhancements in shock assessment, outline USB and safety extra low voltage connector requirements that have recently been introduced, discuss counterfeit and non-compliant USB connections and the ongoing concerns associated with them, run through the constructional safety philosophy for external power supplies, briefly draw attention to rated power considerations, guide instructional considerations, give a rundown of the important applicable safety differences between the IEC 62368 series and the IEC 60335 series, talk about CSA Group service offerings, and finally, offer the opportunity to take any questions.
My name is Nicholas Jones, Principal Technical Lead for Electrical Appliances, and I've worked for certification agencies and manufacturing, as well as directly contributing to both North American and international safety standards for appliances, batteries, and functional safety. I am currently the Head of Delegation for the United Kingdom National Committee to the International Electrotechnical Commission, Technical Committee 61, which covers the safety of household and similar electrical appliances and is responsible for the IEC 60335 series of standards. I am also acting convener of the British National Mirror Committee, CPL 61.
To start off, it helps to have a background understanding of the history of the connection interface. Universal Serial Bus, or USB as it is more commonly known, was established by the USB Implementers Forum that formed in 1995. The technology of USB has evolved significantly since the publication of the USB 1.0 Performance and Protocol-based specification in 1996. Originally only designed for low-voltage data transmission when the initial USB specification was first published, it allowed universal adoption across industry of a common communication means. In addition, it allowed ever-increasing iterative development of interface capabilities as the industry specification has evolved, such as connection type, available power, and data transfer speed, up to the latest USB 4.0 specification we have currently. The industry specification has progressed into separate publications with international standards development organizations, like the International Electrotechnical Commission standards, such as IEC 62368-3, the IEC 62680 series, and IEC 63002, in addition to North American standards, such as UL 9990. While the USB specification was initially limited in scope to low-voltage data transmission, it has slowly evolved to possess ever-increasing power capabilities, currently being able to deliver up to 240 watts, and safety considerations are still evolving with it. This increase in available power allows for greater technological innovation, allowing simultaneous powering and communication with appliances from a single USB port, in contrast to the early days when most USB devices required a dedicated power supply. USB technology has gained widespread use in millions of domestic applications worldwide, including information technology, entertainment, appliances, luminaires, and home healthcare. This is due to its relatively low cost, ease of connection, and universal adaptability. Its versatility includes directly powering devices and facilitating fast bidirectional data transfer in diverse applications without specific pre-configuration. Many appliances are already leveraging USB technology, ranging from blenders, fridges, vacuum cleaners, personal grooming appliances, fans, humidifiers, and even ongoing innovations with high-power applications, such as for powering microwaves. Beyond its conventional uses, USB technology finds new applications in household appliances, demonstrating its role in advancing the functionality of modern appliances. For instance, ovens could receive software updates via USB, allowing them to remain equipped with the latest features and improvements. USB connectivity has also influenced central heating system boiler maintenance, allowing for efficient diagnostics and streamlining updates to enhance and prolong the lifespan of these essential household systems. These examples demonstrate the increasing integration of USB technology, providing not only power and data transfer, but also serving as a conduit for enhanced functionality and maintenance in modern appliances. Modern USB connection methods should adhere to the IEC 62368 series of international standards for audio, video, information and communication technology equipment that will subsequently be referred to as ITAV. The introduction of the USB 3.1 power delivery protocol in 2021, applicable to interface connections such as USB-C, empowers devices with the ability to deliver up to 240 watts by utilizing extended power range, abbreviated to EPR. Verifying safe high-power delivery involves a software-based handshaking procedure which negotiates the power capability of each part of the power system, for example between the appliance, the power source, and an embedded integrated circuit, commonly known as an E-marker, within the cable connector, before the high power is delivered. The IEC 62368 series of end product safety standards not only serves as the foundation of power supply compliance, but also covers the connection of all interfaces used in information technology equipment, including USB, RJ45, RJ11, and similar. Aside from the IEC 60335 series of standards for the safety of appliances, other comparable end product standards determine compliance based on the design and construction principles of IEC 62368-1 compliant power supplies, with only minor modifications, such as specific markings to indicate the intended application. The innovation of USB and its widespread standardization has facilitated product development, particularly in meeting the demands for adaptability and portability. However, this progress has also led to ongoing global regulatory discussions focused on addressing the environmental impact of electronic waste, currently generated by each product having a dedicated power supply supplied with the product. Regulatory authorities have, in some instances, mandated the use of standardized connections that are commonly found in widespread household applications, with USB-C being the preferred choice. Additionally, within the European Union, for example, regulations now stipulate that products like mobile phones must feature a USB-C input for charging, accompanied by the removal of the power supply unit from the product at the point of sale. Authorities having jurisdiction in other countries are now looking to implement similar initiatives. There is ongoing discussion to extend these requirements to other product types beyond information technology, along with specific types of appliances, such as vacuum cleaners. At some point, unknown at the time of this presentation, the IEC 62368-3 standard will be withdrawn in favour of IEC 63315. While technically identical, IEC 63315 has been developed as an independent standard outside of the 62368 series to allow technical committees outside of information technology, audio, and video to reference the applicable requirements. This intentional shift facilitates broader adoption of the requirements across a more diverse range of product categories, such as power tools and appliances. When taking into account end product safety standards found in domestic environments, this presentation specifically considers the IEC 62368 series for IT AV products, the IEC 60598 series for luminaires, the IEC 60335 series for appliances, and the IEC 60601 series for home healthcare, collectively referred to as the similar end product standards from this point forward. All these product types are already commonly found in close proximity within domestic environments. Over time, it becomes increasingly difficult to justify the long-standing technical differences in these similar end product standards, caused from the separation of the standards committees that develop each of them. This is especially true when the products covered by these standards are already using identical technologies and similar use cases. The IEC 60335 series of standards for the safety of appliances adopts a deterministic approach to safety, which means compliance is determined by assuming faults will occur, rather than most other standards that use a risk-based or probabilistic approach to determine how likely something is to occur before the need to consider the outcome. Compliance with standards that take a probabilistic approach, such as the IEC 61508 series and ISO 13849-1, allow risk management to reduce the likelihood of occurrence to acceptable levels. What is acceptably safe to touch varies significantly across standards. In the Part 1 of the IEC 60335 series, being electrically safe for direct accessibility is defined as a voltage limit of up to 42.4 volts direct current and peak value alternating current, with sufficient isolation from mains. Conversely, the IEC 62368 series, focusing on ITAV equipment, introduces requirements for electrical energy source 1, abbreviated to ES1, which permits up to 60 volts DC and up to 42.4 volts peak AC, but with additional considerations for limiting current and frequency to be considered safe for direct contact. As the USB interface is directly accessible to all product users without specific instruction, it needs to meet the requirements of ES1. IEC 61140, the Basic Safety Publication for Protection Against Electric Shock, defines voltage limits for dry locations, but emphasizes additional consideration should be taken into account for wet or highly conductive environments, as stated in subclauses 4.6.2 and 5.3.3.3 of the 4th edition. The IEC 60335 series introduces requirements for environmental conditions by limiting the allowed maximum voltage in specific appliances as a constructional requirement in the applicable Part 2s, and increasing the minimum acceptable creepage and clearance distance across electrical insulation in areas that are likely to be subjected to high contamination, up to pollution degree 3. Pollution degrees are defined in IEC 60664-1, the Basic Safety Publication Standard for Installation Coordination for Equipment within Low Voltage Supply Systems, and Annex M of IEC 60335-1. However, extreme cases of conductive pollution, as categorized by pollution degree 4 in IEC 60664-1, are not addressed, as it has been deemed by the committee as not applicable to appliances, in Note 3 of Annex M in IEC 60335-1. This means within the IEC 60335 standards for appliances, there is no adjustment to the specified safe-to-touch voltage limit in the Part 1 for extreme environmental conditions, such as heavy contamination which may occur from conductive pollution. For example, such conditions may exist if the product is in severe weather, such as snow or heavy rain, if the end user of the product could be wet from a swimming pool, or carrying such contamination on skin from working on a farm. All of these factors could realistically increase the accessible surface area of contact with a potentially hazardous voltage. Specific consideration is also needed in the end product application to whether the user may be wet, as the resistance of the skin also decreases, potentially allowing lower voltages to become more hazardous as they conduct more easily. Some other safety standards, such as the Canadian National Deviations of IEC 60335-1, CSA C22.2 number .23, and UL 1310, address this by halving the accessible allowable voltage limit if the user is considered to be wet. IEC TS 61201 is an application guide for the use of conventional touch voltage limits, and as referenced in IEC 61140, provides guidance for end product committees, though it explicitly notes it excludes considerations for the immersion of body parts. Currently, therefore, there is limited applicable guidance for shaping the end product requirements in conditions with extreme environmental factors. The IEC 60335 series, covering a diverse range of products, includes applications subjected to extreme environmental factors. It covers animal grooming appliances which may be immersed in liquid, debris, or crushed by animals, in addition to electric toilet seats, animal breeding equipment, whirlpool spas, electric fishing equipment, electric fences, and more. Real-world shock is caused by the consideration of many applicable factors, including touch area, skin resistance, electrical frequency, exposure time, return electrical path that completes the circuit, contamination, body parts which the electrical current passes through, the age of the victim, pre-existing health conditions, physiological differences between livestock versus human contact, and more. While this list of considerations is extensive but not exhaustive, it highlights the complexity involved in determining physiological injury. This is the reason why people can still survive after being struck by lightning, even though the voltage of the strike often exceeds 100,000 volts, as the path of current flow and environmental factors is critical in determining the level of physiological injury. Consequently, it is evident that there is still a discrepancy on how the appliance safety standard determines shock and the real-world safety considerations. USB ports that are used on appliances where such conditions exist will likely have to consider the points above in the interests of product reliability and are not likely to be completely covered by the minimum safety compliance requirements. USB ports are commonly found on mobile phones, even when most modern products are typically rated for submersion up to 1 meter underwater. The current carrying terminals of a USB port are typically enclosed by a protective screen and are not normally directly accessible. These devices commonly employ detection features and warnings to notify end users of moisture and dirt ingress, which can become trapped inside the protective screen. Due to the requirements in the IEC 60335 series for accessible voltage, these measures alone would not be compliant for appliances where ingress may be possible, as the USB voltage limits of ES1, which can normally operate up to 60 volts or as a result of single fault conditions, can exceed both the allowable safe-to-touch voltage limit of 42.4 volts and extra low voltage limit, which is 50 volts. This difference means USB cannot by default be classified as either safety extra low voltage or protective extra low voltage. Despite the IEC 62368 series permitting up to 60 volts DC for ES1 limits, the basic safety publication of IEC 61140 restricts this level to dry locations only, in subclause 5.2.6 in the 4th edition. In addition, localized port protection against external environmental factors may be necessary. Solutions like rubberized bungs or screw covers, coupled with clear instructional requirements, can be essential for achieving compliance by minimizing ingress when the port is not connected to an external interface. However, unless a tool is required for removing such covers, these additional port protections are unlikely to help with determining accessibility, as accessibility is determined with detachable parts removed. Consideration of moisture and ingress protection into the interface in all positions of normal use when connected is still required. This may necessitate the use of specialized fixed terminals, locking or screwed interfaces, or other suitably environmentally protected interface enclosures. IP ratings have raised many discussions about safety standards due to the disparity between end product testing and end user expectations. Terms like water-resistant or waterproof imply products remain functional after being subjected to moisture ingress. However, since these terms are not standardized, they may be applied inconsistently to products and still lead to user misconceptions of IP ratings. IP ratings for moisture resistance are usually performed on appliances when they are not functioning, and the assessment is solely based on fail-safe outcomes. The products are not required to remain functional after the test. Additionally, for compliance, only one sample is evaluated, and a determination of ingress is then made on where any moisture is tracked. In reality, especially for portable appliances, potential ingress pathways, including cables, wiring channels, material seams, slots, vents, screw holes, and any surface insufficiently protected against moisture, should be considered for the effects of potential ingress. USB ports can be designed so that only the interface pins are exposed to ingress. Although this limits the assessment, determining compliance can still be problematic. For instance, abnormal operation clauses require single electrical fault assessment, but moisture ingress can effectively lead to a situation where any exposed conductive part can simultaneously short to any other. Even where there are only a few current carrying pins, the number of possible shorting combinations becomes complex. Consequently, ongoing discussions remain focused on improving the standards in this area. Such assessments may result in the port being no longer operable, but deemed compliant so long as an appropriately safe result is obtained. Despite obtaining product compliance, manufacturers must determine if they want the interface to remain functional under potential exposure to extreme environmental conditions. Additionally, it is important to note that not all environmental considerations in the IEC 61140 standard are adopted into the IEC 60335 series. For instance, subclause 5.2.3 of the 4th edition outlines basic dust ingress requirements, IP2X for enclosures of live parts, and IP4X for accessible top surfaces, but it is not adopted into the IEC 60335 series end product safety standards. In fact, there are currently no minimum dust ingress requirements in the IEC 60335 series, even for dust handling appliances like vacuum cleaners. One of the most significant changes in the 6th edition of IEC 60335-1 focuses on new battery requirements, particularly the compliance shock assessment of battery-operated appliances. Previous editions of this standard only considered shock from a single point of contact, which does not exist in an electrically isolated battery-powered appliance. The origins of the IEC 60335 series stem from mains-powered appliances, where a shock risk exists from touching any mains referenced live part and any grounded second point, such as a dishwasher enclosure or radiator. However, when a current carrying point is electrically isolated and decoupled from any other voltage reference, then even under a fault condition, touching any single point of the circuit cannot result in a shock. In situations where an adequately isolated electrical source at any voltage is touched, the opposite supply output from the isolation transformer or DC terminal will simply drift to the potential difference in voltage without causing any harm, even if an external grounded point is contacted. For such isolated sources, the shock risk depends on the insulation between any two accessible points where a potential voltage difference exists. Notably, Annex B of IEC 60335-1, which is applicable to battery-powered appliances, has been entirely rewritten to adapt to this concept. It is important to note that a USB interface, to be compliant, is required to be supplied power from an isolated source. However, it is also important to note that this new two-point shock assessment is confined to Annex B of IEC 60335-1 and is applicable only when evaluating the compliance of battery-powered parts of appliances. Given that the use of USB ports serves a much broader range of applications beyond charging batteries, the current publication requires the consideration of only a single point of contact for any other use during the compliance evaluation of shock hazards. This approach is pragmatic in the context of real-world safety, particularly when external connections may in some way be referenced to ground, similar to a protective extra low voltage circuit when used with a complete appliance. For example, it is possible that for an appliance with multiple USB ports, multiple isolated sources may plug into the appliance. However, if incorrectly grounded, the accessible potential difference between each source could exceed ES1 limits. The risk could also exist if multiple SELV sources are connected in series, or if any non-compliant or counterfeit USB product were connected. The 6th edition of IEC 60335-1 has introduced the first explicit requirement for USB. It now requires both USB and accessible safety extra low voltage connectors to maintain voltage levels within a 3 volts or 10% increase of its no-load output voltage, with the maximum voltage limit being 42.4 volts DC and peak AC. As this new requirement is within the fail-safe criteria, as stated in subclause 19.13 of the 6th edition, it must be checked as part of all required abnormal operation testing in clause 19. For ES1 capable ports, where the limit can be up to 60 volts DC, this requirement places additional compliance assessment for such interfaces, specifically when used within appliances. The interpretation of USB concepts within the IEC 60335 series are still under discussion, as this specific safety standard has always been written on an assumption that if a part or component is deemed critical for compliance, then it must be provided with the appliance. However, with standardized power connections like USB and Power over Ethernet, for example via an RJ45 connector, questions arise about whether external supplies must be provided with each appliance. There are many cases of counterfeit products in global markets using questionably compliant USB connections. Therefore, ongoing efforts in the committee are directed at refining the standards requirements to clearly define safety parameters and the minimum acceptable level of compliance, particularly when dealing with potentially unknown power supplies. Using the communication protocols USB already offers brings the opportunity to introduce handshaking between interconnected parts, especially when compliance relies on specific parts to be used for safe operation. Such an example would be a battery charger where specific circuitry is required to keep the battery cells within manufacturer's specifications, and interchangeability to another supplier's part could impair the safety and even lead to a hazardous situation occurring. Such considerations could necessitate the use of proprietary connections in the design of the product, rather than standardized connections. External power supplies come in various constructional forms, either integrated into appliances or in separate external enclosures. These may include units that are integral to another product, having an enclosure featuring pins for direct insertion into mains power outlets, or in line with cables connected to and from a converter, which is typically positioned on the floor. However, As outlined in the IEC 60335 series, there are many differing compliance considerations for these varying types of construction, with certain constructions not being permitted dependent on the type of appliance. For instance, subclause 24.2 in edition 6 of the Part 1 disallows constructions with switches, automatic controls, and power supplies in flexible cords. Consequently, compliance is immediately challenging for inline constructions with cables connected to both sides. Some designs incorporate a connector on the converter enclosure for one end of the cable, raising questions about compliance. In fact, this question has been raised in Provisional CTL Decision Sheet 2163. The reason for this requirement in subclause 24.2 in the 6th edition of IEC 60335-1 stems from the principle that if a part of the appliance is necessary for compliance, it should be controlled, either by being internal to the enclosure or by not being readily replaceable. In the case of an inline construction, where a part is usually replaceable, this poses further questions regarding an appliance's compliance. Factors like potential tripping hazards, being placed in liquids, or the risk of being crushed by both humans and animals are especially relevant for appliances within the scope of the standard, which experience conditions of use in a wide range of possible use cases. These conditions might be deemed extreme or abusive by other similar end product standards. For example, a handheld hairdryer undergoes much more frequent moving and flexing of a connection compared to a typical personal computer. Some Part 2 standards of the IEC 60335 series have been updated to include specific conditions of acceptability for this type of construction where possible, typically requiring additional testing of the external power supply in conjunction with the specific end product application. In some earlier iterations of the USB interface, incorrect connections were possible, raising inherent safety concerns. For instance, incorrectly connecting a micro USB plug upside down has been known to result in socket damage and burnout. The introduction of USB-C has addressed this issue, ensuring a proper connection regardless of the orientation when mated. When designing appliances, careful consideration is essential for external power and communication signals. Ports that can allow incorrect connection, even if forced, pose foreseeable risks. Product designers must account for this during the appliance design phase. The 6th edition of the IEC 60325-1 standard introduces requirements for the loading of appliance outlet ports to evaluate the impact on the overall product ratings during the power input and current tests in Clause 10. USB, whether implemented as a power input or potential appliance output, requires careful consideration in determining the overall product ratings based on the marked outlet load. To facilitate proper functioning of USB-enabled appliances, instructions should be provided to guide end users of the type of connections, uses, and loads suitable for such interfaces. In this next section, we will explicitly explore the critical differences between the IEC 62368 and the IEC 60335 series of standards and related clauses, focusing on fire assessment, software and cybersecurity requirements, overload considerations, protective impedance, abnormal operation, electromagnetic compatibility, and touch temperature. The assessment of fire risk varies significantly across similar end product standards. Within the IEC 60335 series, subclause 30.2 of the 6th edition requires glow wire material ratings or end product testing at levels higher than comparable end product standards for any areas within 3 mm of a non-permanent, high-power, current-carrying connection, excluding those on printed circuit boards. This is to reduce the initial risk of ignition occurring, tailored to the specific product usage being attended or not, and the amount of current flowing through the connection. The IEC 60335 series does not specify alternative options to the glow wire flammability index and glow wire ignition temperature material ratings, or glow wire end product test for requirements greater than or equal to 650 degrees Celsius. Resistance to naked flame, such as horizontal burn or vertical burn material ratings, are only required for a small part, less than half a gram, or for the material of the PCB. IEC 62368-1 takes a different approach. There is no glow wire requirement for current carrying connection zones, except for switches used as safeguards or in high power applications. Instead, it requires minimum material properties for resistance to naked flame throughout the rest of the product, aiming to reduce the risk of fire spreading. For combustible materials outside a suitable fire enclosure, an allowable option for IEC 62368 compliance is to meet the 550 degrees Celsius glow wire end product test. In contrast, IEC 60335-1 requires this, or an allowable alternative of HB40 rating, for all significant parts of the appliance enclosure. The flammability requirements in the IEC 60335 series were introduced in response to real-world fires involving power supplies for high-power applications in appliances, effectively mitigating ignition risks to acceptable levels. Since USB ports may be left connected and energized without clear indication to the end user, it is an important consideration for compliance to rate such interfaces as an unattended connection means. Although the IEC 60335 series provides exemptions for small parts, such as individually separable parts of the USB interface, thorough consideration of suitable ratings should be explored for all other materials or components that are likely to come within 3 mm of such connection points. When measuring available power within product connections and circuits, it is important to recognize the differing compliance criteria. IEC 62368-1 in subclause 6.2.2.1 of the 4th edition requires an assessment of both normal conditions of the load with the worst case fault in the supply, in addition to the power source operating normally but supplying an abnormally operating load. IEC 60335-1 solely considers the power measurement when each part of the appliance is operating normally. The principles of Power Source Class 1, also known as PS1, in IEC 62368-1, align closely with the low power point determination in IEC 60335-1, as stated in subclause 19.11.1 in the 6th edition, differing primarily in measurement time. IEC 62368-1 prescribes a measurement of up to 3 seconds, whilst IEC 60335-1 requires within 5 seconds, widening the measurement window in which the appliance may draw more power. This difference implies that circuits evaluated as PS1 in IEC 62368-1 may not necessarily qualify as low power points when evaluated to IEC 60335-1. Unlike IEC 60335-1, IEC 62368-1 further differentiates power source compliance criteria beyond PS1 to 2 additional categories of PS2 and PS3, where for instance PS2 must not exceed 100 watts in 5 seconds. In addition, within the required safeguards of IEC 62368-1 to limit ignition from high-resistance connections, there is an additional distinction in compliance requirements for circuits with power exceeding 4 kilowatts, a principle absent in IEC 60335-1. Both standards concur that 15 watts is insufficient energy to pose a fire hazard, exempting the requirements for arcing and ignition for such circuits without any additional compliance controls. A notable difference from IEC 60325-1 is that currently there is no required safety software assessment in the IEC 62368 series for software relied upon for compliance. As discussed earlier in this presentation, current USB implementations rely upon software to negotiate correct power delivery. Contrary, the IEC 60335 series has stringent requirements, drawing from IEC 60730 for automatic electric controls. The 6th edition of the Part 1 now includes cybersecurity requirements, found in subclause 22.62 and Annex U in the 6th edition, not only for safety-related protective software, but also implements the same requirements for software that, if changed, would impact compliance with any major part, clauses 8 to 32, of the applicable IEC 60335 standards. These innovative requirements have yet to be implemented universally across other similar category-specific standards. It is important to highlight that these requirements currently apply to appliances directly connected to a public network. While the USB protocol allows for direct networking when configured as a telecommunication port, its more common uses in the existing market is for servicing and diagnostic analysis of appliances, or for updating embedded software through downloaded software packages onto localized offline storage media. The new cybersecurity requirements do not cover this common use of USB, since it is not directly connected to the public network. However, discussions are ongoing to explore potential adaptations of the authentication, encryption, and error checking requirements that may result in future proposals to cover this use case. A key safety concern is the ability for the user to utilize USB and similar interface ports, as specified in the IEC 62368 series, as a power-consuming input, regardless of whether intended by the product manufacturer. This can result in overloading the power terminals and associated circuitry if not adequately managed. For example, a 5-volt USB port on a battery-powered appliance connected to a 60-volt external power source could lead to a catastrophic overload of the battery management system and may lead to an explosion of the connected battery. Currently, IEC 62368-1 does not specify any safeguards for power supply equipment to prevent power transfer to connected products that are incapable of receiving the highest power levels. It is important to state that the software negotiation is not deemed a safeguard. USB-connected appliances need to self-protect against the range of inputs they are likely to receive from external sources, considering the standardized global usage of USB. Subclause B.22.1 in the 6th edition of IEC 60335-1 introduces a test assuming the range of external voltages can be at least any ES1 level, up to 30 volts AC and 60 volts DC, for elements of a battery charging system, but this does not currently apply to USB and similar ports being used for other purposes. To be compliant to IEC 62368-3, the ES1 output levels must not be exceeded even under the fault conditions of any circuit, with the exception of a basic safeguard, so it is reasonable to consider input voltages up to this level. A basic safeguard in IEC 62368-1 is directly equivalent to the principles of basic insulation or protective electronic circuit in the IEC 60335 series, but not identical technical requirements. In a compliant USB power supply, it is common for at least one Class Y capacitor to bridge the isolation transformer for electromagnetic compatibility suppression purposes. In the IEC 60335 series, this is treated as protective impedance, and two separate components are always required, as specified in subclause 22.42 of edition 6, to be equivalent to reinforced insulation. A single compliant Class Y capacitor and the isolation transformer itself is equivalent to reinforced safeguards in IEC 62368-1. The principle of reinforced safeguards is directly equivalent to that of reinforced insulation in IEC 60335-1. Proposals in the IEC 60335-1 standard are proceeding to allow the direct acceptance of a single compliant Y1 capacitor. This is based on the understanding that such components do not short-circuit when they fail and meet the rigorous component test program specified within IEC 60384-14 to verify this. If this proposal gets accepted, there will be no abnormal operation requirement to consider shorting across the isolation barrier. The secondary side of the transformer is limited by the output of the primary side. The single fault assessment in the relevant end product standards is required for each part of the power supply equipment system, but the worst case output must still be within ES1 limits to be compliant to the IEC 62368 series. The software negotiation of power can be deemed to not be relied upon for compliance if the appliance remains safe for any possible output. Therefore, the Annex R assessment of IEC 60335-1 can be waived if the appliance safely tolerates any ES1 voltage continuously into such ports. In examining the differences in abnormal operation assessments for the similar end product standards, it becomes evident that the standards lack alignment. Despite differences in their structural requirements, key technical distinctions exist. For instance, intentionally weak parts as defined in IEC 60335-1 includes tracks that blow during the abnormal operation tests, but this is not permitted in subclause 6.4.3.2 in the fourth edition of IEC 62368-1. Another notable difference is found in the requirements for single fault analysis, particularly in section 19.11.2f of the 6th edition of IEC 60335-1. This clause requires compliance assessment for the partial turn-on of power switching devices, a requirement absent in similar end product standards. Typically, when power switching devices are shorted, maximum energy is delivered through other components in series with the high power side. The result is normally fuses, PCB tracks, or current sensing resistors blow open circuit, or triggering thermal or overcurrent protection systems before any unsafe condition occurs. Partial turn-on of such power switching components can lead to a state where other components in the circuit, whether safety-related or not, may not have enough energy to trigger open circuit conditions or reach trip limits. However, windings, heating elements, or other parts may still remain energized, potentially resulting in an unsafe condition. This slow blow consideration serves as a test to determine how appropriate safety components are when used within appliances, and if they are specified to reliably operate before any unsafe condition could occur. Additionally, it is a realistic single fault scenario, as a break of the PCB track or solder connection to the gate pin may leave the pin floating. In such cases, stray electromagnetic fields in the appliance environment may couple into the terminal, causing the component to partially turn on. In power supplies, this emphasizes the importance of focusing on the compliance of the transformer, the isolation barrier, and surrounding circuit to determine the appropriate limiting of USB and similar outputs, specifically up to the limits specified in subclause 1913 of IEC 60335-1 under all the possible fault conditions as required in the IEC 60335 series. The IEC 60335 series has requirements that protective electronic circuits be evaluated against electromagnetic compatibility immunity as part of the abnormal operation assessment for compliance, when no similar requirements exist in many other end product safety standards. Note that external interface ports, like USB and others that can be used as telecommunication interfaces, can greatly influence a product's compliance assessment for EMC. Generally, EMC assessment covers both the product's ability to resist electromagnetic interference from external sources, commonly referred to as immunity, and the product's own electromagnetic signals emitted into the local environment or coupled into nearby products, called emissions. In essence, the presence of USB ports and similar interfaces can have a significant impact on whether a product meets applicable standards and global regulations related to EMC. Cross-coupling between interfaces and electromagnetic coupling paths in and out of products, along with adjacent cabling, demands careful consideration for any filtering or shielding that may need to be implemented. Touch temperature limits are carefully defined in the IEC 60335 series and are stricter in most cases than similar end product standards. Additionally, there are variations in the probes used to assess which points are measured. These differences have evolved over years of addressing the dynamic settings within and around users' homes, workplaces, and public spaces. It is necessary for the appliance standards to cover the diversity of user demographics exposed to the associated risks of appliance usage, from infants to the elderly, and with varying levels of capability, training, and experience. IEC 62368-1 adopts Test Probe B from IEC 61032, which is the basic safety publication for the protection of persons and equipment by enclosures. However, it also adopts a jointed test probe normally only associated with North American standards, which is not defined in IEC 61032. The IEC 60335 series generally leverages test probe B to determine accessible surfaces of parts, with additional specific probe requirements existing in some Part 2s of the standard series. Extensive efforts have recently been made to provide clarity across the Part 2 standards. For external power supplies, these differences are unlikely to have a significant impact. However, given the varying limits across Part 2s of the IEC 60335 series, direct compliance comparisons are challenging and must be assessed on a case-by-case basis. While the landscape of compliance and standardization for USB-enabled appliances and external supplies remains complex, with numerous technical questions yet to be addressed across the similar end product standards, manufacturers can confidently navigate the compliance requirements with the support of an accredited third-party testing and certification service provider. As a global testing and certification service provider, CSA Group can help manufacturers gain an in-depth understanding of global regulatory requirements that impact their products. Accredited by OSHA, SCC, and many other authorities having jurisdiction globally, we offer extensive testing and certification services aligned with the applicable standards, such as the IEC 62368 series, the IEC 60335 series, and the IEC 60598 series. Leveraging over a century of curated expertise, coupled with CB testing laboratories strategically positioned across North America, Germany, Taiwan, India, China, Korea, and Singapore, we possess the necessary capability and capacity to seamlessly facilitate your compliance journey. As the regulatory landscape evolves, you can rely on CSA Group to be your trusted service provider, providing the guidance needed to navigate compliance challenges associated with today's USB-enabled appliances.
Thank you very much for your attention. Now is an opportunity to take any questions you may have.
Oh, there we go. Okay, so thank you. Many thanks to Nicholas for that highly informative and insightful presentation. I'm sure everyone will agree. We have learned a lot about USB technology and the compliance challenges. So I think without further ado, we'll launch straight into the Q&A. We did get questions throughout the session, which Nicholas kindly answered. But please do feel free to ask any other questions that you may have, because now is the time. Oh, okay. So we have got a question that has just come through. Are certified recognized components USB controllers available? What standard would these be certified to, and would they be acceptable in both 60335 and 62368? Or any other standards such as for lab or medical equipment? I will just publish that as well so you can see.
Yeah, it's a very good question. And I just want to start by saying thanks for everyone who has already posted questions. I think they've been very interesting already. And you've obviously liked to put me through my paces of them. I appreciate that, only too much, because I know how much of a wide-reaching topic this is. So obviously is of interest to a lot of different industries. To kind of pick up on that exact question, the end product standards, particularly IEC, I would say rely on less the component certification and more the end product application. So it really is dealt with in a end product use, and whether that is acceptable would determine, particularly in 60335 series of standards, what that end product is. So if you take something like a portable handheld hair straightener, the requirements to that could be quite different from, say, an electric fence. Because the use case, the environment, the exposure of that interface is application specific. So it must be considered on that case-by-case basis.
I hope that answers your question. Do we have any more?
There was one I'd like to pick up on from Thomas,
Yeah.
if I may. Thomas is raising some interesting questions around the first numeral of the IP rating. So I briefly mentioned that in the slides, that we don't really have specific requirements that they are even needed in IEC 60335 series of standards today, not in the most part. So really it would come down to consideration of what the appliance was if it were marked. Simply to reply to the question, it isn't actually required to be marked in most cases that I'm aware of anyway. It's certainly not required in the part 1 for it to have a first numeral of the IP rating. So I hope that answers your question, Thomas.
Thank you, Nicholas. So while everyone's just thinking of some other questions, I have got a question for you myself. So you spoke about the evolution of USB technology. What do you think will replace USB? And if something does replace it, what will the implications on the testing certification industry mean?
Well, that's a very interesting question, actually. I think the analogy I would use is something like the more proprietary options that we've seen manifest more commonly. So if you look at something like the Lightning connector, it's actually now, I would say, more towards being phased out, but that's because there's a regulatory implication mandating the use of, today, USB-C for some types of applications. I think we will see probably, my expectation anyway, is that more regulators will get involved in those discussions, mandating the use of USB in future technologies, whatever they may be. I would say from a safety compliance point of view, we care less about the interface and more about what's driving that interface. So even if you look at something like RJ45, commonly called Ethernet, if you look at RJ11, which is typically found on things like old school telephones, the power supply is the same in most cases for all of those interfaces. So I think to try and broaden the topic and try and focus less on the interface and more about the safety considerations that drive that interface really is the key to tackling this well. So we don't get too hung up on just calling something USB-C when tomorrow we might get USB-D, E, F, G, H. Who knows?
Brilliant. Thank you so much, Nicholas. And out of curiosity, do you think there should be more regulation? And do you think regulation could improve or disadvantage things? If you were in charge of regulation, what would you do?
I'm going to have to slightly caveat any response at this point to say I'm not a regulatory expert by any means. I'm a compliance member for the committees, and the regulations and standards, I would say, go hand in hand, but they're not directly related. So regulations always sort of trump the voluntary requirements of international standards. So really, that's a question for the regulators, how they want to handle it. I guess there's certainly that sustainability piece, which is a key part of those discussions, driving less proprietary interfaces and sort of more promoting the widespread use of those standardized interfaces. I think that's really where a big opportunity, both from a regulatory and from a standards development side, so that we're not too focused on traditionally ITAV applications, looking more at the wider use of where USB could be used, could be mandated in specific applications, and making sure that those have the suitable requirements, at least in the safety standards, to adequately address any questions that arise about its application. And as you can hopefully see from my slides, that there's a lot of work still to be done there.
We did indeed. Thank you so much. We actually have got another question as well. So if USB-driven product for IEC 60335-1 can be tested and certified without USB charger?
That is correct. Yes, it can. If it was a USB interface, purely powering and driving that product with or without a battery, we do have a classification in 60335. We would call them a class 3 appliance. We do have some requirements, but there are certainly still questions within the committee itself about further developing those requirements for the modern applications of the USB interface, which go beyond traditional views of just being 5 volts and low current. We're now seeing much more development in the interface itself that allows much higher capabilities to directly power even high power applications in appliances, and that with it brings further questions where we still have more work to do.
I really hope that answers your question, Arun. And we do have another question here as well. So what are the more practical consequences of the current mix of USB requirement in the market, like a luminaire used with an ITB USB power supply?
That's an interesting question. I'm going to struggle with some of that, but I guess there isn't really a limit, is probably how I would answer that. There isn't any set hard limit about how far you could use USB. And really that is really where we have questions, I would say, the most questions in the committee, because USB isn't just used for powering, it's data transmission bidirectionally. So every combination of that can exist, whether it's just outputting data for a data logging purpose or to provide information to another part of an appliance, whether it could be powering an appliance, whether it could be doing both, for instance. So really, we need to make sure that we've got that understanding and considerations in the standards for all of those uses. And I would personally say I don't believe we've got that fully covered today. So really, we've got more work to do. And really, that's where I see the questions are still rising, and rightly so. So let's see how we can develop those requirements over time.
Amazing. So really quickly, if you do have any other questions, please do ask them now. And just to let everybody know, the slides will be available after the live broadcast, and also the recording will be made available as well if anybody does want to go back and rewatch it. We do have another question. If a manufacturer wants to go over and above the 60335-1 safety standard, what would be the industry best practice approach using 13849 or 61508 or some ad hoc alternative?
Well, specifically, the standards reference lead me to believe that there's a question of the software, because those standards are particularly applicable to the software development. Oddly enough, I happen to know those questions are even going on in the ITAV committee. And so we're seeing further development about where that's going to go. Just with my TC61 hat on for a moment, I would say 60730 is a good one, because that particularly is where we get our requirements for software controls, the single fault analysis, and the other functional safety requirements in appliances, and all the associated controls come from 60730 as our sort of primary source. Which is a sort of dissemination of 61508 that was referenced before. So really, I would start there if you're going to talk about appliances. And I know that there are ongoing conversations even in the ITAV applications about the acceptability of that. So I would say we hope there'll be future work in those standards committees to help write those requirements adequately in the international standards.
Perfect. And we have another question here from Vijay. What efforts are underway to harmonise the IEC standards?
Well, we've had long standing liaisons with all the committees for a long time, and in fact, the committee for appliances has recently gone through a massive restructuring effort, mainly because of the amount of work we've got just purely from existing amount of different varieties of appliances and new ones that are coming. So I really think that restructuring should lead to better harmonization of applicable areas. So for instance, if you've got a desk lamp and it's sat next to a heater, for instance, then why should those requirements be any different? For instance, they're sitting side by side on your desk at home. So that provides an opportunity for those groups of technical experts to have that greater collaboration, where previously we didn't have those opportunities before. So I think I would say, just frankly speaking, we probably haven't had enough up till now, but really my hope is that moving forward, we will have that much greater collaboration.
Perfect. We might have time for maybe 1 or 2 questions. I can see we do have another question. The interpretation of Class 3 appliances is different between different test houses. Does CSA have an acceptance paper for this?
So it's not an acceptance paper. We do look at the application specifically for things like battery operated appliances, and we do write internal requirements, I would say, to evaluate those requirements if necessary. So there isn't one that I'm aware of specifically for the topic of Class 3 appliances. It's certainly on the radar of keeping an eye, but it's more application specific than it is just calling it a Class 3 appliance level, if that helps.
Amazing. Perfect. I think that might be all the questions. I just want to say a big thank you to all the questions that have come through, because we've had quite a lot. So I do hope that all questions have been answered and you are happy with the answers there. Thank you so much, Nicholas, for joining this webinar and giving such an amazing presentation. Again, very interesting questions, and many thank you for your responses. And thank you so much to our audience for the great questions and the level of engagement. And once again, thanks to everyone for joining us here on this Consumer Electronics Testing and Development webinar platform. Like I did say before, the webinar will be available to rewatch, and the slides will be available if you do want to refer back to that. So I wish everyone a very pleasant evening.
Thank you very much for hosting, Manny, and thank you everyone for attending. I hope you have enjoyed the presentation, and we look forward to answering any further questions if you have any. My email is on those slides, and feel free to reach out.
Hello.